These days, variations in computer architecture has settled down quite a bit. We don't often talk about whether a modern computer is 32-bit or 64-bit or anything like that. Pretty much because everything except the absolute tiniest of devices are all 64-bit, and there's, even across different processor families, there's a lot of architecture uniformity. Now, this has not always been the case, and through the ages of retro computing, our chosen hobby, this conversation has come up quite a lot.
16-bit sports action.
If we're going to talk about 32-bit versus 64-bit, or even 16-bit or 8-bit, we should first talk about what a bit is and where it comes up in computer architecture. So what is a bit? A bit is the fundamental atom of digital computer storage. It can represent a 1 or a 0, on or off, true or false. That's it. Now, a single bit by itself is not terribly useful, and it is very common to gather bits together into chunks that will be treated as a single value. Some number of bits grouped together, we'll call that number n, and treated as a single value can represent a range of values from 0 to 2 to the n minus 1, which is 2 to the n distinct values, because 0 counts. So if you grouped 3 bits together to form a single value, they can represent numbers from 0 to 7, which is 8 possible values. Now, it's also possible in a few different ways to interpret these as signed values. That is a massive side tangent that I'm going to try real hard to avoid for the purposes of this video.
As the internet age emerged, chaos ensued.
In so many ways, the early days of computing were just the absolute Wild West. One of those ways is how computer architectures gathered bits together to form the values that are the fundamental data types used in programming. For example, in this 10th printing of the 1978 edition of the C programming language, it says that the Honeywell 6000, a computer I've never seen in real life, used a 9-bit byte, and every other data type, with one exception, was 36 bits. Very early IBM System 360 computers used a 6-bit byte. Since the mid-1970s, things have settled down quite a bit. The 8-bit byte that we know and use today had pretty much taken hold as the standard. And for the most part, people would refer to 8 bits as a byte, 16 bits is a word, 32 bits is either a double word or a long word, depending on whether or not you grew up with Intel or Motorola. Most commonly, a 64-bit value is a quad word. Those were not often used in the old days. The IBM Power CPU architecture refers to 64-bit values as double words, just to be IBM about things. And there's even one goofy architecture that calls 64-bit values a phrase. Yay for standards. There are a few places where this comes up in computer architecture that are going to matter for the purposes of this discussion. These are register size, ALU width, data bus width, physical address size, and virtual address size.
The upgradable Intel 486 processor.
Registers are the fastest memory available on a computer. On every processor architecture that I'm aware of, at least some of the values involved in a computation, like addition or multiplication, have to be stored in registers. So the size of the registers effectively sets an upper bound on the size of computations that can be calculated efficiently. Closely related to register size is the arithmetic logic unit width, or ALU. That's the part of the computer that's actually doing the computations. Now, the ALU width and the register width don't necessarily have to be the same. They can be, either can be larger or smaller. I'll talk a bit more about this later, but for example, on the 68000, it has 32-bit registers, but its ALU is only 16 bits. It can perform many kinds of 32-bit computations. It just has to cycle through the ALU twice to do it.
In 4 64-bit 66 megahertz PCI slots.
The data bus is how all data gets loaded into the CPU. It's very common on older CPUs for the data bus to be much narrower than the width of the registers, or sometimes even the width of the ALU. The 68000 has 32-bit registers, but it only has a 16-bit data bus. It's possible to load 32-bit values. The CPU just has to cycle through 2 bus transactions to do it, so it takes longer. On more modern processor architectures, it is very common for the data bus to be much, much wider than anything else on the architecture. The DEC Alpha 21064, which is not modern by any stretch of the imagination, had 64-bit registers and a massive 256-bit wide data bus. Now, these super wide buses are generally used to very efficiently load data into the on-CPU data cache. Yet another topic that could be a video all of its own. I did touch on this a little bit in a video that I did about slot 1 CPUs maybe a couple of years ago. I'll put a link to that up above. I probably could have lumped physical address space and virtual address space together, but they're different, and some of those differences will be a little bit important later on in the video. Virtual address space determines how much memory a single application can see. This does not have to be physical RAM. This can include like a page file out on disk or other virtual memory scenarios. Physical address space is how much memory can actually be wired up and connected to the CPU. And these can be different in either order. So either one can be bigger or smaller than the other. Both combinations happen in real life. For example, the Pentium Pro has a 32-bit virtual address space, so applications can see 4 gigabytes, but it has a 36-bit physical address space, meaning you can actually connect to the CPU up to 64 gigabytes of RAM. In a single user kind of home computer, this isn't terribly useful having this disparity, but this processor was designed for server systems where a lot of applications might be running on a single system, and having each application be able to see 4 gigabytes of a giant 64 gigabyte mass could be tremendously useful. Now, the Pentium Pro just happens to have 32-bit address registers, and that exactly matches the 32-bit virtual address space. But this also doesn't have to be the case. The 68000 also has 32-bit address registers, but it only has a 24-bit virtual address space. And this difference caused a lot of problems when early Macintosh and Amiga users upgraded from 68000s to 68020s, but that for sure is a topic for a different video.
Since the network is the computer has to be sunk.
So what makes a system 64-bit or 32-bit or whatever? You're going to hate this, but it's complicated. The commonly accepted definitions today center around the sizes of 3 different aspects of the system architecture. And these waters can be muddied a little bit by the operating system running on the system and its application binary interface. And the capabilities of a system can be artificially limited by the operating system that's running on it. So for example, if you put Windows 2000 on an Athlon 64, as a lot of people did when those CPUs first came out, it's still going to appear as a 32-bit system, even though that processor is fully capable of 64-bit. There are also some quirky, goofy, and I do not mean that as an insult, ABIs like X32 that sort of run the operating system in 64-bit mode, but run applications in a sort of 32-bit mode. And these special purpose ABIs generally exist for performance and efficiency reasons, for applications that don't actually need the super large address space afforded by a 64-bit system. The three values are the integer size, the long integer size, and the pointer size. In some rare cases, one case, and I'll get to this later, we have to drag in another size to identify the platform, and that's the long integer size. I don't know of a long integer size, but I'm sure its time is coming. Generally, two of these things will have the same size, and that's how we'll identify the platform. For example, if a platform has a long integer that is 32 bits and a pointer that is 32 bits, we'll call that platform LP32. If the regular integer size is also 32 bits, we'll call that platform ILP32. I suppose it is possible for all three values to be distinct, but I don't know of any such architecture. If you know of such an architecture, please let me know about it in the comments. How does this relate to any of the sizes that I mentioned before? Well, typically, not always, the integer size will match the ALU size of processors used in the platform or the processor originally used in the platform, which may have set the ABI in place. For example, the 8088, 8086, and 286 all have a 16-bit ALU, but the 386 has a 32-bit ALU. On DOS, all of those CPUs will have a 16-bit integer, even if the 386 is running in 32-bit protected mode. Int will be 16 bits. However, on Linux or BSD or other Unix-like operating systems, the 386 will have a 32-bit integer. You may recall that I said it was complicated. Regardless, across all those platforms, when running in 32-bit mode, the 386 will have a long integer that is 32 bits, and the pointer will be 32 bits. So the 386 is at least an LP32 platform, depending on the ABI. Now, Windows has an exceptionally long legacy that stretches all the way back to DOS. In Windows NT, I'm not sure about Windows 95. I'm not familiar with that platform at a programming level. It was created as an ILP32 platform. When it was eventually extended to 64-bit era, pointer had to grow to be 64 bits, but to maintain backwards source code compatibility, they decided to keep long integer as 32 bits. But they needed an integer type that was 64 bits to match the pointer type, and you wanted to be able to do 64-bit calculations, so we'll make a long integer, and that will be 64 bits. So to this day, Windows running on 64-bit is LLP64. Long, pointer, 64 bits. For some purely practical reasons, even architectures that really want to have all values treated as 64 bits will have integers as 32 bits. I don't know of any architectures in common use that are ILP64. Wikipedia article mentions that the port of Solaris to the HAL SPARC 64 processor is ILP64. It seems like there would be some serious software portability and interoperability issues on such a platform. If you ever developed software for the HAL SPARC 64, I would love to hear about it in the comments. I suspect there were some challenges, and I would really like to hear about those. But I think we have enough of a framework in place that we can draw a line in the sand, and we can say that any platform that is at least LP64 or LLP64 is 64 bits. And if you're not at least that tall, you do not get to get on the 64-bit roller coaster. All right, well, let's look at some classic examples that people in retro computing might care about. I'm gonna look at a bunch of examples from pretty ancient to fairly modern, maybe around where we would kind of cut off calling something retro. I am not going to look at the most ancient examples. I'm not going to talk about super old mini computers. You can go to Usagi Electric if you want to hear about old mini computers. I'm also not going to talk about the 4004 or the 8008. Those don't really come up that much in typical retro computing sorts of conversations. Our first example is the venerable 6502. Has an 8-bit ALU, 8-bit registers. The pointers, I guess you would say, are 8 bits. It's kind of a weird architecture. The bus is 8 bits. The virtual address space is 16 bits, and the physical address space is 16 bits. Through the use of bank switching, a lot more memory could be accessible. I mean, the Apple IIc shipped with 128K of RAM that was accessed by bank switching. And, there were multi-megabyte upgrade adapters available for the Commodore 64. But there's still only 16 wires that come out of the CPU that connect it to RAM. Everything else was some other external thing giving you additional power. I'm going to call it 16-bit. I don't know how to designate a 6502 in this nomenclature. You wouldn't really want to run C on it. It is not an architecture. I know that there are C compilers for it, but it is not an architecture that is very friendly to C's model of the world. And so using this kind of naming on it, I'm going to leave that entry in the table blank. I don't know what to call it, but it is widely accepted as an 8-bit CPU. So we'll call it, it's an 8-bit CPU. But here's where things will get a little bit weird. The Z80, also an 8-bit ALU. The registers are 8-bit, but pairs of registers can be used together to create 16-bit values. A similar technique is also used in the 8086, but I'll get to that. Pointers are 16 bits. Address bus is 8 bits. Again, this has the same 16-bit physical virtual address space and the same goofiness with bank switching. We're going to just call it 16-bit. Now, I guess you would call this an LP16 architecture, but it's an 8-bit CPU. Like, it's an 8-bit CPU. I feel very weird about this table entry. I don't know how to reconcile this line with my view of the world. 8086, 16-bit ALU, 16-bit registers. Now the 16-bit registers on the 8086 are kind of similar to the 16-bit registers on the Z80, except instead of thinking of it as combining two 8-bit registers, the model on the 8086 is more like splitting up a 16-bit register to get two 8-bit registers. It's kind of effectively the same, but the mental model of it is different. Now, pointers on the 8086 are super weird. In most programming models on the 8086, pointers are 16 bits. But they also get combined with another 16-bit value somewhere else to make a 20-bit value. Because that totally makes sense. Now, and in some programming models, you keep those two 16-bit values together, so you've got 32 bits, but it still gets combined by the CPU to make a 20-bit value. Okay. The virtual address space is 20 bits. The physical address space is also 20 bits, but through a technique called EMS, which I have covered in previous videos, additional memory boards can be put into a computer to effectively do bank switching to give access to up to 32 megabytes. But again, because of how many wires actually come out of the CPU, I'm going to call it a 20-bit address space. And I guess the entry for an 8086 would be IP16, and it's a 16-bit CPU. The 8088 is essentially the same, except its bus is only 8 bits. They cut out some wires to save some cost. But it's the same architecture. It has so many of the same characteristics. Even though its bus is smaller, it's not reasonable to call it an 8-bit CPU. The 286 keeps up a lot of the same trend, 16-bit ALU, 16-bit registers, the same, I don't know what you call them, 16-bit pointers, 16-bit bus. It has a 20-bit-ish virtual address space because of a weird quirk of how those two 16-bit values get combined to form a 20-bit value. The virtual address space is technically 1 megabyte plus 64K. So I don't know what to call that. Weird. I'm going to call it weird. It's 20-bit. We'll call it 20-bit. The physical address space of the processor is 24 bits. So the processor can be physically connected to more memory than a single application can access. It is the first of many processors to behave like this. As far as I know, there was some other processor that had that same sort of virtual address space being much smaller than the physical address space. I would like to hear about that. I would like to learn something new. And again, I think the 286 is safe to call IP16, and it is definitely a 16-bit CPU. Now, the 386SX, which I have heard some people call the 286 Pro, has a full 32-bit ALU. It has what we now think of as protected mode, 32-bit mode, and in that mode it has 32-bit registers, 32-bit pointers. The bus is 16 bits, like the 286. The virtual address space is 32 bits, and the physical address space is 24 bits, just like the 286. I would call this platform LP32 or ILP32. It's going to be the same in that respect as the 386 that we're going to see next. It's a 32-bit platform. Now the 386, Intel's first true 32-bit platform, 32-bit ALU, 32-bit registers, 32-bit pointers, 32-bit bus, 32-bit virtual address space, 32-bit physical address space, and as we previously discussed, LP32 or ILP32, depending on the operating system that you're on. For sure, 32-bit CPU. Now the Pentium also has a 32-bit ALU, 32-bit registers, 32-bit pointers, but it has a 64-bit bus, and its bus got wider specifically to be able to fill its L1 caches much more efficiently than on the 46 that came before it.
That's the power of the Pentium processor.
32-bit virtual address space, 32-bit physical address space, and again, in spite of the 64-bit bus, this is going to be LP32 or ILP32. It's a 32-bit CPU. Nobody would argue that the Pentium is anything other than a 32-bit CPU. The Pentium Pro continues right where the Pentium left off. 32-bit ALU, 32-bit registers, 32-bit pointers, 64-bit bus, 32-bit virtual address space, and as I had previously mentioned, a 36-bit physical address space giving access to 64 gigabytes of RAM. It's still LP32 or ILP32, depending on the ABI, 32-bit CPU. Even though it's got a 64-bit bus and a 36-bit physical address space. No one's going to say, well, it's a 36-bit CPU. No, it is a 32-bit CPU. Switching gears slightly, the 68000, which is the first processor I ever really programmed on, 16-bit ALU, 32-bit registers, but you can use the bottom half of the registers as 16-bit values. It's not quite like on the 8086 where you can split and independently talk about the top half and the bottom half of the 16-bit registers as independent 8-bit values. You can just look at the low 16 bits of your 32-bit register. Pointers are 32 bits, the bus is 16 bits, the virtual and physical address spaces are both 24 bits. This is another weird one that makes me feel a little bit uncomfortable to say. This is an LP32 platform. Long integers, 32 bits, pointers are 32 bits. There's no other way to name it, but it's a 16-bit CPU. So this is another CPU that we see where sort of the designation for it is one size and the practical way that it is called is a smaller size. 68020 extended the 68000 to a full 32-bit ALU, same 32-bit registers, 32-bit pointers. The bus is finally 32 bits. The virtual and physical address spaces are now also 32 bits, and this is where some platforms that use the 68000 started to get into trouble because people said, I mean, the CPU is only going to look at those 24 bits. I have these other 8 bits. I can put stuff there. And the CPU just ignores it because it's only a 24-bit address space. And then you run that application that has garbage in those upper bits on an actual 32-bit CPU. Kaboom. And again, 68020 for sure legit LP32 or ILP32, depending on the operating system. It is a 32-bit processor. MIPS R3000. Now, variations of the R3000 were used in a wide variety of disparate platforms, from early workstations running Unix-like operating systems from SGI and DEC, all the way to the original PlayStation. Got a lot of mileage out of that CPU architecture. 32-bit ALU, 32-bit registers, 32-bit pointers, 32-bit data bus, 32-bit virtual and physical address space, definitely ILP32, 32-bit CPU. SPARC v7, which was the first commercially available SPARC architecture. Earlier versions of it were purely in academia. Again, a topic for a totally different video. 32-bit ALU. One thing that was very common across early RISC processors is every ALU instruction had to take the same amount of time to execute. And multiplication is hard. To do a 32-bit multiplication in the same amount of time as a 32-bit addition, it takes a lot of transistors. It takes a lot of transistors, and they didn't have that kind of real estate available, so a lot of those CPUs did not have a full 32-bit multiplier. They had some kind of 16-bit multipliers where you could multiply two 16-bit numbers to get a 32-bit partial result, and by doing a couple of those, you could do a full 32-bit multiply. This is still common today. There are a lot of GPUs, for example, that don't have a 32-bit integer multiplication. You have to do several 16-bit integer multiplications to produce a full 32-bit value. 32-bit registers, 32-bit pointers, 32-bit bus, 32-bit virtual and physical address space, and again, like the MIPS R3000, ILP32, 32-bit CPU. PowerPC 601, the first of the PowerPC line. There were power processors before it, but it's the first the PowerPC line. 32-bit ALU, 32-bit registers, 32-bit pointers, 32-bit bus, 32-bit virtual and physical address spaces. I'm starting to feel like a broken record. ILP32, it's a 32-bit CPU. No one argues that. MIPS R4000, credited with being the first 64-bit CPU. 64-bit ALU, 64-bit registers, 64-bit pointers, 64-bit address bus. As far as I could tell, it had a 40-bit virtual address space and a 36-bit physical address space, LP64, 64-bit CPU. The first of its kind. NEC created a derivative CPU based on the same architecture called the VR4300, and a version of that was used in the Nintendo 64. 64-bit ALU, as far as I can tell, the version used in the Nintendo 64 also had a 64-bit ALU, but I couldn't find any documentation to confirm that. The quirky bit is the Nintendo 64 SDK generates 32-bit binaries, so architecturally the same kind of binaries that would have been on the R3000. The reason that they did this is because the Nintendo 64 had so little memory, you didn't need 64-bit pointers, and so just having all of the pointers take up twice as much space when all those upper values were going to be 0 seemed kind of wasteful. And RAM was at a premium on that system, so the binaries were all created as 32-bit. You could still use 64-bit types, and presumably the 64-bit ALU would do the 64-bit adds in a single instruction cycle. 64-bit registers, 64-bit pointers, again, unless you're creating binaries for 32-bit mode, in which case the pointers would be 32-bit. 32-bit bus, I believe it was a 64-bit virtual address space, as far as I could glean from the documentation that I looked at, but it was a 32-bit physical address space. Again, I would say running in a 64-bit ABI, LP64, it's still a 64-bit CPU. So a person could legitimately call the Nintendo 64 a 64-bit system. I would not argue with them about that. Now, a processor that I am personally a big fan of, the DEC Alpha 21064, 64-bit ALU, 64-bit registers, 64-bit pointers, a massive, I still can't get over this, 256-bit data bus. It's so huge, but it's used for filling the enormous cache that many of those CPUs had very efficiently. 64-bit virtual address space, the hardware documentation that I could find says that Alpha CPUs must have at least a 43-bit physical address space. And there are different versions of it that do different things, so I'm going to say 43 bits. Unarguably, LP64, a powerhouse of a 64-bit CPU.
Digital presents the metamorphosis of a total solution that uniquely combines two recognized world leaders.
The UltraSPARC, which was Sun's first 64-bit CPU, 64-bit ALU, 64-bit registers, 64-bit pointers. It also had a giant 256-bit data bus. I couldn't find documentation for the original UltraSPARC, but the documentation that I found for the UltraSPARC 2 said that it had a 44-bit virtual address space and a 41-bit physical address space, so that's what I'm going to put in the table. Again, LP64, 64-bit CPU. Last but not by any stretch least in this table, the IBM Power 3. Now, the Power 3 wasn't IBM's first 64-bit CPU in this architecture family. That was the PowerPC 620, but that was a complete commercial failure. So I would rather talk about the CPU that was a commercial success, as it had more impact on the market. 64-bit ALU, 64-bit registers, 64-bit pointers, 128-bit data bus. Quite a lot was said by IBM in various technical reports and other conference presentations and things like that when the Power 3 was coming out, bragging about its 128-bit data bus and how efficient it was. I find that interesting because it had been preceded in the market by several processors that had much wider buses. So I'm not 100% sure what they were bragging about. 64-bit virtual address space, 40-bit physical address space, LP64, 64-bit CPU. I'm going to stop there with examples of real CPUs. That's obviously not all of them. It's not even all of the important ones. I didn't talk about anything from HP.
Piranhas are power-packed with two industry-leading PA8600 RISC processors.
I didn't talk about Itanium. But I think it covers a lot of the important examples that people will care about in the retro community from the 70s up through the 90s. Now, if you're still with me at this point, I would really appreciate it if you would take a moment to click the like button. And if you're interested in this sort of weird, technical, quirky, retro content, I would highly recommend that you click the subscribe button, because I'm going to keep making more stuff like this. Let's talk about a hypothetical example and how it might be classified. Say it's the 90s, and we're going to make a new RISC CPU for embedded-ish applications. Now, like many architectures of that era, we're going to give it 32-bit registers, 32-bit pointers, and a 32-bit ALU. But like other RISC CPUs, we want every instruction to take the same amount of time to execute, and multiplication is hard. So we're going to give it an instruction that will let us multiply two 16-bit values together, produce a 32-bit result. And to help optimize that, we'll add another instruction that lets us do the multiplication and an addition in the same cycle. Fast memory is still pretty expensive, so to keep overall system costs down, we're going to design the system around somewhat slower memory. But to keep performance up, we're going to do two tricks. The first thing is we're going to give the CPU a 64-bit bus. And second, to utilize that 64-bit bus, we're going to add two instructions to the processor. We're going to add a 64-bit load instruction and a 64-bit store instruction. And we'll design these so that the load will read 64 bits of data from memory and store it into an even-numbered register and the following odd-numbered register. And the store will kind of work in the opposite way. It'll take an even-numbered register and the next odd-numbered register, and will write its contents out to memory. Now, again, because memory is expensive, we don't expect to ever be able to afford, much less need, more than 16 megabytes of combined RAM and ROM. You got to have some system ROM to boot up from. So we're just going to give it a 24-bit address space, both physical and virtual. To me, this looks like a blending of the previous table entries for the 68,000 and the Pentium. I don't think anyone could make a case to call this anything other than LP32 or ILP32. I feel very comfortable calling this a 32-bit platform, except I've misled you. This CPU does exist in two slightly different forms, and both of those forms are in this Jaguar console. This is a 32-bit platform, except some clowns in the marketing department at Atari got it in their heads that because there's 64 bits somewhere, we're going to call it a 64-bit platform. Now, they had a problem. They had a very real problem that they needed to solve. See, they had been beat to market by two other 32-bit platforms. And each of those platforms had a pretty significant feature that the Jaguar didn't have. Both the FM Towns Marty, which if you don't live in Japan, you've probably never used one, and the Amiga CD32 both came out before the Jaguar. They're both very capable 32-bit platforms, and they both had CD-ROMs. And Atari needed to find some way to market their 32-bit platform as better than their competitors' 32-bit platforms. So they just tunnel vision fixated on this 64-bit thing. And they had this huge marketing campaign around the 64-bit issue.
Let's review the numbers. Sega Genesis is 16 bits. 3DO is 32 bits. The Atari Jaguar is 64 bits. Which is more advanced? Clifford!
Why would I buy a 32-bit system for $300 when I can get a 64-bit Jaguar system for $149?
I spent a brief time in 1994 and 1995 working at a game company developing software for the Jaguar. I was young and foolish and in way over my head. All the projects I worked on got canceled. But I very clearly recall all of the programmers at the company complaining just about how asinine all of this 64-bit marketing campaign was, that it was just... Folks, repeat after me. After doing plus the equals math, the Jaguar is not a 64-bit platform. Now, have a very happy April Fool's Day. And until next time, try to remember the good stuff. These muddies can be what? These muddies. 128-bit. 128-bit data bus. Oh my gosh. I'm a mess. 128-bit data bus. Oh my god. 128-bit data butt.